Good day to you. This is Galactic bringing you another science adventure in geometry, not very commonly taught or presented these days, but geometry, of course, is well known to us all, at least in theory, at least in the abstract. Over here you'll see a list of terms which I've put together in order to indicate a sequence that I will be following in this presentation, in order to give a definition of geometry, in order to introduce a relatively new concept in geometry, which is the difference between two types of geometry, which was never known until this millennium. Geometry, of course, goes back to the time of Euclid and before, approximately 2,500 years ago. So it's a very old concept. It is linear geometry of which we speak when we speak of Euclid. I'll be covering that in order to give that geometry a definition, so we'll have a working definition which has been checked, but you should check anything that you don't find perfectly acceptable. Perhaps you have a different concept, and as a scientist you have to challenge anything that some presenters, such as myself, tries to foist on you as the definition of geometry. Well, it can be approached in several different ways. But to get right into this, we do have at the top of this list, first of all, the date, May 29th, and then geometry, which I believe needs to be explained, or at least defined in some sense, in two ways. The line is the basis of Euclidean geometry, which we will define and, of course, cover, but only in summary fashion because we're attempting to get to the bottom of the list, which you can see changes in color at the bottom. We're getting there, but the line, as Euclid defined it, is based on the point, and you'll see that I have that highlighted in blue background, the point, and then the plane, which is a very important geometric object. All three of those items, line, point, and plane, are considered to be geometric objects, which we will also define very briefly because you probably already can make the definition in your own mind from memory or just from common sense. What are the objects used in geometry? After that, we introduce a very well-known term which is related to geometry, and that's the concept of numbers. A very basic concept. We'll simply introduce a simple definition of numbers. And then we need to understand the operators. Really, there are two pairs of operators, as we're all taught in grade school. Addition with its complement, really its additive inverse, subtraction, and then multiplication and division, which were usually taught in that order. So those would cover the operators, which turns out to be an important concept to bring back to mind. As we discuss the role of numbers in geometry, it has a lot to do with the operators. After that, you'll see a bold italic term, conjugality. Holy smokes! Once you see words starting to get longer and longer, more syllables, this could raise a sort of a yellow flag, like, whoa, this is all I need is to learn some new terms. You may already know what that word means. It is essentially a mathematical term, but it also has a geometric connotation. And what is it, just simply, in case you've never encountered that word or it slips your mind what exactly it means? Conjugality is comparable in terms of how to define it. You would want to compare it with polarity. Polarity, I think we all know what polarity is, but just as a reminder, which is important just to bring these things to mind, even if we know them all already, in a presentation it's important to set the definitions that we'll be using, simply to bring them to mind if for no other reason, but there are other reasons. Conjugality is not this. This is plus minus. It's associated with a line that is polarity. There's a plus pole and a minus pole. On a line, you wouldn't normally say pole, but the concept is polarity, two opposite linear directions. So that's very elementary. But then conjugality is then easy to at least portray geometrically. Remember, we are discussing geometry primarily. If you start with a point and you go into opposite directions, that's polarity. But if you go into perpendicular directions, that yields conjugality. So you may know about the right angle law, usually called the Pythagorean theorem. That has to do with the conjugation of the vertical line with the horizontal line. Now, you may wonder, what does this have to do with anything? It's important to get the definitions first. Just bear with me. This should not take long. We only have 4 more terms to discuss, just to bring them to mind. Asymptosis may be unfamiliar to you. It's not a tremendously advanced term, and you probably have heard of it before, the asymptote, which is a relationship between two types of line. Asymptosis refers to something we're going to see visually in a moment. We will have some diagrams coming up in order to show what an asymptotic curve looks like. It does refer always to a curve, but it's a curve in relationship with a straight line, with a very interesting property that exists, really a relationship that exists between the two lines. In this case, calling the curved line a line because you can draw them. And there are different definitions of the line, which, as you can see, we already have a 2 after line. And I'm just switching over to that screen. I believe you can see right here, I'm highlighting it, line has a 2 after it because we have 2 definitions of line that need to be merged, even as geometry will have 2 definitions which merge, just to make things simple. It's very important to keep things simple in science. So there are black colored terms. Then we have 3 terms which are in red. And the reason I put them in red, I think you could probably guess from the first term, infinity. Infinity is a most interesting concept. And we will talk about that again briefly. This is an introduction to geometry in order to disclose a relatively new discovery in geometry, which goes right to the basis of geometry. I should probably at least mention what that's going to be that I will be broaching to you. I would assume for the first time, because it appears that I discovered this. Although the concept or the conceptual terms are already known. So what is it that I'm leading up to? It is important to broach that early in a presentation so that you have some expectation. And I may have delayed too long, forgive me. I'm still learning how to do science presentations. I've only made 1,600 and some videos over the past 4 years. But all on my own. So I'm basically learning from my own work, which that's what you have to do if you're flying solo. Now, the last 3 terms begin with infinity and then imaginarity. Now, imaginarity may not sound like a geometric term. It is, but that is part of my discovery of what that is. Now, imaginarity does occur in mathematics. And mathematics is implied in our item numbers. Really, numbers and operators, that constitutes mathematics. But imaginarity is very interesting to try to define. And you may wonder, does it even have a definition if it's imaginary? So imaginarity is a concept which has been used in mathematics and really has been explored in geometry. You may have heard of the complex numbers, which is a two-component number system where one of the components is considered to be real, which is a kind of linear number. And the other number is very interesting. It's based on a different metric, where, without going into that in detail, the complex number system uses a two-componency representation of a single number, which has two numbers that conjugate. Very interesting, because we talked about conjugality just a moment ago. And the final term, hyperspace, is relatively new, although conceptually it's existed for well over a century and a half, really going on 2 centuries now. Hyper simply means a higher linear dimension than 3. 3 is the number for volume space, as you know. 2 is the plane, and 1 is the line. Technically, the point is 0D. So this is the dimensional system of the linear, it's called the linear systematic space, because it has 5 levels currently. You may realize immediately that we have gone to the 4th linear dimension. It wasn't Albert Einstein who discovered that, but he's the man who certainly made it famous, because space-time is a 4D formulation. So hyperspace, generically speaking, just as you could say a superclass term for kinds of hyperspace. There are different kinds of hyperspace. And we'll talk about that. So that completes our list in summary fashion without having given you too much information. This is quite necessary in a strict scientific, that is, the scientific presentation sequence of something new does require a proof, which may be a brand new proof. If it is a discovery, which I claim to have made, a very simple discovery in geometry that breaks geometry into 2 parts. You may know that geometry has been broken into parts in different ways, which is one reason why we want to be sure we know what we mean by geometry. That could be considered a simplistic term, but when you're talking about a new kind of geometry, it's important to know what the old kind is, so that you can have a basis for considering a new geometry, which is really a new kind of geometry, but actually it is a new geometry. I discovered a new geometry. That's what I'll be proving to you today in this video. So to begin at the top of the list, we have geometry, which I claim has 2 definitions. And at this time, according to the strategy I'm adopting in this video presentation, I'll be reading from a prepared script, which I won't burden you with on the screen, since it's actually rather difficult to read text on a video screen, especially if you're using a cell phone. So don't worry, the diagrams coming up throughout this video to come as we proceed will be highly explanatory. Geometry is a highly visual science. So to begin, I'm just going to read and make notations on what is geometry. What is it? And this I call the outline of physical geometric mathematics, because we're going to encompass this whole list under that rubric, that is, that title. This is physical space that we're trying to match. And that would be spatial space that we see all around us, although we actually see through it, correct? Very interesting to try to characterize space geometrically. Albert Einstein certainly did a good job by extending 3D to 4D in order to incorporate a perception of time that is conjugal with space. They are conjugal, and I'll be showing you that. All right. So this is the outline of physical geometric mathematics. We will be talking about the number system associated with Euclidean geometry, really just simple linear numbers. All the numbers that we ordinarily use are linear numbers, and I'll show you why you have to say linear numbers. You may know the complex numbers are not linear numbers because they have two componency, whereas linear numbers have one componency. When you have a number, you don't need to take it apart. A complex number, you do need to take it apart, and then you need to put it back together again. We'll talk about that. That may sound a little vague, but this is the introductory section. We are necessarily being just a bit vague until we put everything in a row so we know where we're going in this proof sequence for a brand new geometry, which I hope you enjoy. I've gotten a big kick out of this since I discovered it 4 years ago in 2022, at which time just a few months later, it was January that I felt that I had made this discovery, and it was June, I believe that's 5 months later, or 6 months later, I started this channel, which is called AE. All right. Now, geometry and numbers are directly related. They are related on a differing representation. What do I mean by that? They are related on a differing representation in the sense that numbers relate quantities. That's fairly obvious. Numbers, in essence, in their original use, represent quantities. And that's not what geometry does. Geometry does not represent quantities, but of course you immediately see there's an overlap. And that's very important to understand the relationship between geometry and numbers, which is really geometry and mathematics, which goes forward to geometry and algebra, which we're now going to talk about. So we have one definition of geometry, that it does not deal with quantities. What does it deal with? Geometry relates structures, and that's the introduction of our word structure. Structure and geometry, of course, are intimately related. Geometry is essentially the study of structure in a structured way. Generally speaking, we begin with the line. That's what Euclid began with. In order for him to begin with the line, he found it necessary to axiomatize a point, which he didn't really define except in terms of the line. And when you don't define your base term, that's called the axiomatic term. It's part of the system that Euclid is generally accredited with having discovered, the axiomatic system of logic, which has to do with how you begin. And he wanted to begin with a line, but he deduced or figured out before he wrote Elements that he would have to introduce the point first, for a very simple reason. He already saw in his own mind that the line, in order to be computable, in order to be useful really for distance, it would need to be made of points. That's actually quite profound, but it has stood the test of time for about 2,500 years, so I don't think you and I need to question that. We will return to that point, pardon the pun, it's an inevitable pun, and I'm used to it now, I hope that doesn't confuse you. We will return to that point, which is the point, which is the point. All right. The next item down is the plane, and we're going to get to that now that we have at least talked about the line, which we haven't defined yet, and you see there's a 2 after line. But have I shown you both definitions of geometry? The way that I want you to think of geometry is what it is and what it's not. Geometry deals with structures. It does not deal with numbers. So accept that for now. I began by stating that geometry and numbers are directly related. We need to be absolutely sure we know how that is done. And that has to do with an interesting topic called metricization, which is the application of a metric to a geometric object, which we know from grade school can be done with a line. When you start by putting a 0 on the line and you start counting by equally spaced units, you're metricizing the line with linear numbers, 1, 2, 3, 4. And that can be said to go to infinity, because there's nowhere to stop unless you cut off the line, making it a line segment. And strictly speaking, the line, as we are taught it, and how mathematicians and really physicists, everybody uses the line, it's bipolar. Remember that that's polarity. So when you take a distance, you're only taking a distance in one direction. Distances are always positive. Now, it's important to note, at least if this has never been directly pointed out to you, that Euclid, indeed the Greeks, and indeed all mathematicians and geometers, until centuries after Euclid, did not have a concept of negative numbers. And in fact, they did not have a concept of 0. They only had a concept of positive quantity, which in Euclidean geometry, as Euclid published it in Elements, is distance. Distance. So that's a linear concept. All right. I think you can tell we're getting to nonlinearity. That's the essence of my discovery, a nonlinear geometry, which is a term which has been used before, because it has been at least intuited that physics sure could use a nonlinear geometry. Is that possible? It hasn't been possible until very recently. I believe that I have discovered this, a nonlinear geometry. In order to explain that, and in fact to prove that it does exist, we do need to go through this sequence. I hope this is not tedious. I have been practicing for 4 years to be sure that this is not tedious. This is supposed to be fun. I really stand by that statement. All right, so geometry does not deal directly with numbers. It deals with relationships between structures. And a line is a structure. Technically, it's an object, which doesn't mean that it's something you can hold in your hand. It means it's something that you can visualize. And the simplest of all geometric visualizations is the line. The point is a little bit problematical, and we're going to come back to the point in a moment. But we just want to breeze through this to show the relationship between all these terms so that they all fit into a certain perspective, really into a framework. All these terms are related. They're related geometrically with a numeric, that is a mathematic basis. Mathematics, just to go a little step ahead, mathematics is essentially, I should say, it can be defined as the necessary tool to prove geometric statements. That might be challenged, but I think you can see that that is a reasonable thing to say. That mathematics is the servant of geometry. That statement can be defended. It could also be debated. That's okay. We don't need to worry about that. I just wanted you to know my frame of mind so that you'll see better, more clearly, where we're headed, which is the world's first non-Euclidean geometry. That statement needs to be defended because there have been claims, really going back 2 centuries, that, for instance, Lobachevsky, and another, for instance, Bolyai Janusz Bolyai, and Nikolai Lobachevsky are very famously touted to have discovered the world's first non-Euclidean geometry. It turned out to be not as useful as one might expect from, I would say, the hype, but those were very important discoveries. And Lobachevsky and Bolyai essentially discovered the same thing virtually at the same time, one in Russia, really central Russia, and the other one in Transylvania, which at the time was part of the Austro-Hungarian Empire, but today is part of Romania. So that's where those two men lived. They were not in direct communication, but they both discovered what was called non-Euclidean geometry. I have given video presentations on that if you care to look in the archive. Leave a comment if you would like to find that video, or if you would like me to review those videos. There's more than one on non-Euclidean geometry in the Lobachevskian and Bolyayan sense, which Gauss claims to have figured out before both of them, but without offering any proof. Gauss is highly reputable, so he probably did. He claimed that he did not publish because he wasn't certain about what he had seen, which Bolyai and Lobachevsky did publish about, and Gauss actually started to learn Russian because he was so fascinated with Lobachevsky's discovery that he wanted to understand Russian so that he could understand Lobachevsky. Very interesting anecdote, which I just throw in because this is a human endeavor. We're supposed to be having fun. I just consider that to be a fun fact to know and tell, so forgive me. Now, to sum all this up, we want to go through this sequence now that we've introduced all the terms, all the way down to hyperspace, which I think you now understand is simply a higher dimensional space than 3D. Now, imaginarity we also covered. That has to do with... Actually, imaginarity comes up in several contexts, and it may be the most, I would say, far out concept in this list. But the one above it is well known to everybody: infinity. Infinity. I didn't really comment on what is meant by that, except on a line. You can see that it goes to two polar infinities on the line, which is an object which now constitutes a space. And this is a specific geometric use of the word space, that a line is an object because you can draw it. That's the easiest way to say what an object is in geometry. It's something you can draw, or at least project, because you can also draw a sphere, but you can't draw a sphere on a flat surface without shading and other effects, which we're all familiar with, so we can visualize a curved line and a three-dimensional object. Those are all valid objects. But each one of these objects represents a space. And that's a very interesting term, space, because the line technically is a 1D space. And this will have an effect on our definition of numbers, because it was proved in the 20th century. This may be the first challenging statement. You may want to look this up, but I'm going to tell you what my research reveals. In the 20th century, for the very first time in the history of mathematics, the definition of a linear number was finally closed. So we have a closed, coherent, consistent, complete, the four big C's, a closed, coherent, consistent, and complete definition of what is a linear number. That was discovered by a man whom I call my teacher, essentially for this reason, John Horton Conway. John Horton Conway, probably most famous for having discovered the game of life, which is really fascinating, but he actually was a little resentful, and he expressed this in more than one interview, that he was sick and tired of being remembered for having invented really this video game, is what it amounts to. Look into that if you're interested in the game of life, and you may find out why this is just an ultimately amazing little game that he invented. But it's also not really what he did. He was very much into games. But John Horton Conway invented a number classification system using a binary tree representation, where using this tree, called the surreal number tree, he was able to prove what is a linear number to completion, which not even Cantor could do. None of the mathematicians all the way through to the time of Conway, in the second half of the 20th century, Conway published his N0 system. N sub 0 is what he called it. Donald Knuth of Stanford, a legend in computational science, and one of my teachers in my industry where I made a living as a computer scientist. Everybody knew who Donald Knuth was. He is still alive, by the way, and he got a hold of Conway's small publication, publishing his tree, which John really didn't push this very much. He just published that he had made this tree. But Donald Knuth realized, as I later realized, this was absolutely a major breakthrough in mathematics. And it's just amazing, just one short anecdote again, that Conway discovered this method of proving what is a linear number because he was trying to understand the Oriental game of Go, G-O. And if you've never heard of that game, and many Westerners have not, I've played it for over 50 years. I play it almost daily. It's an addicting game, very much like chess in its own way. It's a skill game, but he was trying to understand the game of Go. And from doing so, he ended up with this binary number tree. And Donald Knuth read the paper that John published and gave a name to this number system. It is a valid number system for a most interesting reason. I should say part of the fact that this is a bona fide number system is because it captures in this tree the definition of every single linear number system. And there are between 6 and 9 linear number systems. This is an interesting classificational problem. The real numbers you've heard of, but you've probably heard of the rational numbers. There are algebraic numbers. These are all subsets of the linear number system. But nobody ever defined what is a linear number in the broadest sense of any linear number system must be based in some common feature which would define that number for any of the subsets. That was never done until John did it. But in order for him to complete that work, he had to capture all the infinities. The line is overloaded with infinities. These are essentially what I would call transcendental numbers, although that's not technically the right word, but they're non-repeating decimals, which is called an irrational number. The simplest irrational number is 1 over 3. Because the decimal representation, that is a computer representation of 1 over 3, cannot be made exact. It's a repeating decimal. It's 0.3 but it has a bar over it because it's a string of threes, which means it goes on forever, which means it's not a quantity. Except that for now, that can be rigorously proved, but it's not a difficult proof. A non-terminating number cannot be said to be a quantity because you can't count it. That gets into some really interesting philosophy about what is a number. But John solved everything. There are an infinity of infinite numbers, that is, non-repeating decimals, such as 1 over 7. 1 over 7 is actually a repeating decimal, but it's an order 6 repeating decimal. It's 0.14285 6, and that repeats. If it's rounded up, it's 0.142857, and that's simply to round it off, and I believe that is the 6th decimal place. It could be the 7th. I'm not going to bother with that right now. Leave a comment if you want to correct me. But I think you see the point. There are repeating decimals such as 1 over 3. There's another kind of repeating decimal represented by 1 over 7. Also 1 over 11. But then 1 over 37, just to give an example, is a non-repeating decimal. So is pi. So is e. And you may be able to name some others. Non-terminating decimals. Okay. Decimal, by the way, is simply a notational system for numbers. You can also use binary, and we're getting to that. That is another valid it's actually a subset of the linear numbers. The binary numbers are a subset of the linear numbers. That's commonly stated, but again, you may have some questions about a lot of these things. We're starting to get into the reason why nobody could ever define what is a linear number. It's because there are so many irrational numbers on the line, including pi. Pi is one of the most important numbers that's ever been discovered. Now we're getting to that. So now we have geometry defined in two ways. It's not quantities. It's not quantities. And that's the first definition, which is negative. It's not really saying what it is. It's asserting what it is not. It's very important that geometry is not about quantities. What is it about? That's why I wanted to have two definitions, so that you would be forced to ask that question. If geometry is not quantities, which is the province of numbers, arithmetic, mathematics, and algebra, that deals with quantities, although algebra starts to work in structure. And really, you could say that the operators introduce some structure, because now you have a relationship between two numbers on an operator. And that is a relationship. But you see, the relationship always has that equal sign in there, such that 2 plus 1, you could say that relates the two numbers together, 2 and 1, on addition. But really, there's another symbol there, which is not a mathematical symbol, it's a relational symbol. The equal sign balances the two quantities. And that's why it's so important to have the concept of quantity in the number. Well, geometry does not deal with quantities. It deals with structure. And structure is a very abstract term. But the important aspect of using that word, structure, is that it doesn't have to do with quantities. What does it have to do with? Relationships. But these are structural relationships, such as the relationship between two orthogonal lines on the diagonal, which gives us the right angle law, also called the Pythagorean theorem. Probably the most important, historically, the most important equation of all time. It's where we get sine and cosine from. I don't think I need to say more. about the importance of the geometric concept of the relationship between two objects, really, more generally, the relationship of structure, the relationships involved in structure. That's geometry. Now, the line, I now want to go into a bit more detail to explain, again, as you probably already know, but I think I'm going to give you a bit of added information on what Euclid said that is fully accepted. Nobody has ever challenged what Euclid said is a line. And I don't challenge it either, just so you know ahead of time. The line, the way he stated it in the first two sentences of Elements, the most famous book ever printed. Outside of religion, you might have to have a footnote, but it certainly is the most famous book of all time in science, is Euclid's Elements. And there he begins with a definition of a point. And the reason he introduces what he wants to define, which is the line, is that he realized he could not define the line the way he intended unless he had the use of the word point. And by doing this, it's really a step backwards. He wanted to talk about the line, but in order to do so rigorously, provably, so that anybody could follow what he said or says and repeat everything that he did, he realized that he had to define the point, because essentially the line, the Euclidean line, the line that Euclid wanted to define, is not continuous. It's actually quantized. It's quantized on the linear metric, which is distance, which for him was strictly positive. So we're talking about a ray. That's the term that I was taught in school, and I'm sure you were too. Because it's not a bipolar line, which has a negative direction, which is fully accepted now. Euclid had no concept of that. There's no such thing as a negative direction in Euclidean formulation. It's only distance, which is always positive. There were no negative numbers in Euclid's day. So when he defined a point, what he was doing was making an axiomatic object in order that it could componentize the line. In other words, he wanted to define the line as being made of points. That the line, the Euclidean line, is made of points. So it's extremely important to get the exact definition of a point. A very interesting exercise of the mind, which I'm just going to bring forward. This is not old hat to anybody. This is something that has baffled men. What is the definition of a point? Well, what did Euclid say? That would be the final authority. What did he say? He said that it's 0D. It has no dimensionality. There's no dimension to a point. He didn't say 0 because he didn't even have that concept, not as a number. So what did he say? He stated that the point lacks all three systematic linear directions, which is polaric this way, then polaric this way, which is orthogonal, and then polaric orthogonal to the other two orthogonal lines, so that all three lines are mutually orthogonal. Very important, because that's why we are constrained to use the Pythagorean theorem to get a position on a plane and a position in volume space. You must use the Pythagorean theorem, which is the sum of squares. And just to jump to space-time is linear systematic space as well, except it's 4D. So as well as the three lines that make volumetric space is what it's called, so you can get a position in volume space, on the Pythagorean theorem, which is simply x squared plus y squared plus z squared. Americans would say z squared, and I am an American, but internationally, everywhere except America, it's z, just so you know. You may already know that. So x squared plus y squared plus z squared equals the square of the distance. The square of the distance. So to get the distance, you have to take the square root of the sum of squares. And that's called the Pythagorean theorem in volume space. Now in space-time, you do exactly the same thing, except you're adding 4 orthogonal lines, one of which you can't visualize. It's imaginary, which you can see that brings in our concept of imaginarity. So Albert Einstein, in his formulation of space-time, introduced a 4th orthogonal vector, which was already known to Minkowski and Poincaré and a few other. This had been explored, so that was known that you could do that. And it was even known that you could use that in order to relate time to space. Strictly speaking, Albert didn't discover that. His teacher did. And you can study that if you wish. That actually is still somewhat debated because of the tremendous profundity of what Albert introduced, which was a formulation of gravity. The Einstein field equation, which formulates relativity into an equation that can be solved, that geometry is called spacetime, and it is a hypercubic geometry, which reintroduces our last name term, hyperspace. Spacetime is a kind of hyperspace, and now you know why the hyper is in there. It's because when you go beyond 3D to 4D, as Albert did, you're introducing imaginarity. So we're kind of going back up through the list now. Now you have a more clear perception of why I introduced the term hyperspace. It's because space-time is a hyperspatial system. Very interesting to know exactly what that means. We're getting there. Oh, you're going to understand everything there is to know about general relativity and space-time from the ground up. This is how to do it. And then we're going to go beyond it. That's what I discovered. So this is highly profound. I hope you're getting excited. This is supposed to be fun. Oh, it is. I swear on that. You know, I don't want to introduce as swearing like, oh, my soul is on the line. But I'm just telling you, this does go somewhere. It should be interesting anyway. I hope you enjoy this so far. I'm very sensitive to, I want this to be interesting, not tedious. All right. So now we've come to the plane. Now the plane is also a geometric object. Why? Because you can visualize it. Actually, that's rather a profound statement. Physiology in the 20th century, that is physiologists, have proved that that is how we see. We see a plane. And that's why we understand a movie as representing reality. You actually can't tell the difference. There's a footnote there. But we do see a planar image in our brain, in our mind. So you also see depth. That's true. And that's so interesting. How do we see depth if what is portrayed in our mind is a flat screen image? That is a plane. So this is a very powerful object, the plane. A piece of paper or a chalkboard is a planar surface. I think I need say no more about the profundity of the plane, but it's neither a point nor a line. However, what you can say is that when you make a line, you're drawing it on a plane. And when you make a line, it is made of points. So this is a hierarchy now. This is the introduction to linear systematic space, which begins with 0D, the point, which technically then is not even there, but retroactively it makes a position, and that's the value of the point. It's a position on the line. So that is the point. It's a position on a line. That is called a point. What is the definition of a point? That is the only definition of a point. There is no other definition of point. It does not exist unless it's on a line. Accept that for now, or think about it, or ask a question in the comments. But that actually can be proved. I proved it, although it has been proved before I did. So that's not a discovery of mine, although it's very close to what I discovered. So now we have the point is 0D. The line is 1D. Why? Because it has an extent. Well, then you have to ask an extent where? Technically on the plane, but that's also retroactive. A line can be oriented, obviously, in any spherical direction. Just you have a line going through a point. Well, you can spin that line in any number of ways. Spherically, actually. But on a plane, you can only rotate the line in a circle because it's got one less degree of freedom, because the plane constrains what you can represent about the line. But the line still can be rotated in any planar direction. Right? That's very important. So the plane introduces the concept of a movable, that is a reorientable line. If you just have a line and you don't say where you're drawing it, which is how Euclid did it, then the line is simply by itself. It doesn't have an orientation. It's a space. And it makes a space by itself. It's a line. What's it made of? Points. And what's a point? They are objects that are not actually there, unless they're on a line, in which case they are actually there. Why? Because they're separated from each other on the line. Very interesting. I hope that makes you think. But all of this is 2,500 years old, so it's not like I'm making up these fancy puzzles to baffle your mind. It's just that it is very interesting. I hope you agree. So what about the plane? Well, the way the plane can be metricized, the line is metricized with linear numbers. 1, 2, 3, 4 makes distance. On the plane, you now have more than just one direction. You have another direction which would be vertical as opposed to the horizontal. Well, that's magic, because the plane, if you draw a line on the plane, it can be proved that you can draw another line that bisects, they bisect each other, but they are perfectly related on a symmetry. I think you can see that it makes 4 quadrants. That's because when the horizontal line is stretched to its 2 polar directions, this would be horizontal left and right, you could say. Left and right. And then you take another line and you go perpendicular. That's the perpendicular relationship between 2 lines, which only exists on a plane. That is the basic definition of what is orthogonality or perpendicularity. It's 2 lines on a plane that are absolutely balanced. you can't draw this line and then just make kind of an X. That's called affine geometry, when you're not, strictly speaking, relying on orthogonality. But that's not how science developed. And affine geometry, so far, has very little application, although there are some cutting-edge scientists, including, I'll just say, well, I don't want to name drop, but there are several very prominent mathematicians who are attempting to use affine geometry to make some kind of breakthrough. It hasn't happened yet, but it's still being very strongly studied. We will not be dealing with that, but it's in all the textbooks that affine geometry is a more abstract, really it is a hierarchically higher classificational term for a family of possible relationships between two lines on a plane that intersect. They're not skew and they're not parallel. They intersect on a plane. Well, on a plane you can prove that either the two lines that you draw are either the same line, called the identity relationship, which is kind of moot, but it's always stated in a rigorous proof. But if you have two lines that don't intersect, therefore they're parallel. Now in volume space that's not true, because the two parallel lines may look parallel, but if you look from another angle, the line that looks like it's parallel is actually skew. Without going into detail, I hope you can visualize that, but we're talking about the plane and how to metricize the plane. In other words, to extend the concept of distance to something on a plane. That is, between 2 points on a plane. Not just 2 points on a line. That's distance. 2 points on a line in Euclidean geometry makes a distance, which is a quantity based on the metricization of the line, which are equally separated points. And they are separated. Is there anything in between them? Yes. And that's called the quantum jump in linear space, which can be conceptualized as the jump from 0 to 1. Is there anything in between that 0 and 1? No, there's not. Cantor argued that until it drove him mad, and he died in an insane asylum. Nobody can prove that that's what drove him mad, and I really doubt that it was, although it might have. But everyone's wondered about it, and there's a reason why men have wondered if that drove Cantor mad. It's because he was attempting to do the impossible. Because in order to have a metric for the line, in other words, to get distance, you have to have a quantum jump from 0 to 1. It's just a question of how small the jump is. But if you don't have a separation between the 0 point and the first distance point, called the index of the metric, is 1. By definition, that's mathematically axiomatic. That's how we use the number 1. That it's the smallest jump in space, in linear space. That is 1D space. It's the smallest jump that you make to get the metric. For instance, the distance to a star has to be in units separating points, which therefore have a space in between them. Well, that space is actually the distance. So isn't that interesting? That the distance from 0 to 1 is 1. But there's nothing smaller than that. And Cantor argued with that, and it's still being argued. What you're trying to do is de-quantize the line, which means you're trying to make it continuous. And it's artificially stated now, as if this were a law of the universe, that the real number system captures that. That the real number system is continuous. It's a continuous linear number system. I think you see now that that's a mistake. That's an error. There is no such thing as a continuous linear number system, and there never will be, because by definition there cannot be, or you lose distance. That cannot be argued. That's bottom line. So the Euclidean system is very interesting. It has 5, as of the 20th century, it has, really as of the 19th century, it has 5 objects. A 0D object called the point, a 1D object called the line, a 2D object called the plane when you use 2 lines to metricize the plane, a 3D object, which is cubic space. Instead of being squared, the plane is being squared. That's why we have so many squared terms in mathematics, such as c squared. The speed of light squared? Why would you need that number? Very interesting story, which I've solved. And that's part of my discovery sequence. Oh, it goes quite deep. But when you get to 3D, you now have cubic space. And once you go to space-time, you have hypercubic space. None of which incorporates curvature anywhere. And we'll come to curvature in a moment. And you'll see curvature is actually on this list. Asymptosis is a form of curvature. So we're getting there. We've gotten through geometry, and we have the 2 definitions. It's not quantities. It's relationships of structures. The line is what? It's made of points, but the only reason it's made of points is to get a metric called distance. And that's where you get the strange number 0, because you can't measure a distance to anything, not even a star, unless you have a 0 point in order to make the jump to your index. And that's called the quantum jump. And that will be enough for now. I'll have another video following this. That's 1 hour. After editing, I'll be able to cut this down. It's actually 1 hour and 2 minutes. And I don't want to go over an hour because this is heavy stuff. I think you agree. Thank you for tuning in. This is I've been practicing to do this for 4 years. That is no exaggeration. I've produced over 1,600 videos in order to achieve the ability to make this proof sequence for you. You're going to learn a ton along the way that you never learned in school. Some of it's been proved, and it does exist, it's just rarely talked about, such as the value of 0. Does it even have a value? We're going to get to that. We're going to cover all these terms, and we're going to go on to curvature space. All right? Thank you again for tuning in. This is Anagalactic, bringing you the secrets of the universe, this time in geometric form, which is how you get understanding. Nobody ever got any understanding from numbers. Take it from me, I'll prove that to you. The only way to get understanding in science is from geometry. Numbers will mislead you. Stay tuned. We'll be right back on this 29th day of May 2026. Thank you.